those terms are too ambiguous for you. Never mind. By the end of my presentation, you will become somewhat of an expert in this field. Now, where and how did soldering begin? Some historians trace soldering back to the time of Egyptians. Some traced it back to the time of the Mesopotamians. But nonetheless, we know for a fact that civilization began in present-day Middle East. What did they use soldering for at the time? At the time, soldering was being used for jewelry making. Soldering was being used for warfare as well. They made their spears out of it, they made their swords out of it, they made the wheels on their chariots, and even the shields for warfare, as I said. So now the method they used was very crude, as we can see, but it was very applicable. It was only some 5,000 years later that tin was discovered, and the discovery of tin changed the whole soldering game. Soldering stopped being used just for simple applications such as metal joining. It evolved into more complex applications, just as we see in our PCB boards that are in our computers, laptops, etc. Now, if you're familiar with solders, you will know that lead-present solders have been completely eradicated from the microelectronics industry. Why so? Why have they been eradicated? This is because, on disposal, lead-present solders were very toxic to our environment. They killed the fishes in our oceans, they polluted the waters in our homes, and even caused severe ailments to we humans. Now researchers had to go back to their papers, and alternate solder had to be found. The criteria for this solder was they had to be of low cost and they had to have low melting temperature. A couple of solders were discovered, such as tin argentum copper, tin zinc bismuth. For my research, I used tin zinc bismuth solely because it had the lowest cost and lowest melting temperature. Now, you may be wondering, how do fluxes come into play in the process of soldering? Well, I remember being in the lab one day while soldering, and I thought to myself, what if I don't use flux to solder my solder specimen? So I thought to myself that, okay, I'll use flux for some and not use flux and compare the results. So I ended up not using flux for one of the specimens. As soon as I finished soldering, I picked up the specimen and it fell right apart. I didn't have to apply any pulling force, it fell right apart. Now, flux is that fluid that strengthens and facilitates the soldering process. There are three types of flux. As I just said, there are three types of flux. There's the water-soluble flux, there's the RME flux, and then there is the insoluble flux, which is also known as the low-solid flux. On application, all these fluxes vary in characteristics. So now in my experiment, I experimented with all these fluxes and tested the strength of them using tin zinc bismuth solder alloy. Before carrying out the experiment, I firstly measured, using an electronic balance, the composition of my tin zinc bismuth. After which, the composition is then placed into a crucible and then placed on a hot plate, and the temperature of the hot plate is cranked up to about 450 degrees Celsius and left on for about 2 hours, so this mixture is homogeneous. After the mixture solidifies, it is then compressed using an hydraulic press to a thickness of 1 mm. After it has been compressed, we now have a thin sheet of solder, which is then punched into tiny billets of 5 mm radius. It is at this point that we can now use the solder billets to solder up our specimens together while applying flux on the surface. Now, the application of flux, as I said, will strengthen the solder joint. And we'll see the same for the shear test specimen, but the only difference is that it is placed in a lab joint. And then, after we carry out the process for all of these specimens, we're now ready to test our specimen using the universal testing machine. The specimen is placed in between the claws of the universal testing machine and pulled at a constant rate until it fails. At this point of failure, we can then take our measurements and observe using an optical microscope. Now, using an optical microscope, we can then see the surface of each specimen. Now, let's observe the surface of the tensile test specimen. We can see, for the low solid flux, as I mentioned earlier, we have a huge fracture on its surface. And we also have a dimple, which is quite huge on its surface as well. For the RMA flux, we have a slightly smaller dimple. And for the water-soluble flux, we have the smallest dimple with no fractures on its surface. Now, before I draw a conclusion, let me use this analogy. Let's say I had two pairs of hands, and I had this plastic ruler and this metallic ruler. If I use my first pair of hands to pull onto this plastic ruler, and I use my second pair of hands to pull onto this metallic ruler, logic tells us that this plastic ruler will budge first, right? This is because the material this has is a lot stronger than the plastic material. So before I finally draw my conclusion, let's observe the shear test specimen. For the shear test specimen, we see a huge dimple on its surface. And then we see a slightly smaller dimple, as I mentioned earlier, on the surface using the RMA flux. And the water-soluble flux has the smallest dimple. Now we're more critical, so we incorporated a more sophisticated machine, which is the SEM, scanning electron microscope machine, to go deeper into the surface of the materials. Now at 50 times magnification, we can then view the surface of each of these specimens. Now we can see the pores on the low solid flux, which is quite huge. And we see dimples on the surface of the low solid flux. Similarly, a large pore on the RMA flux, but the water-soluble flux has the smallest pore on its surface. We then went further to 100 times magnification, where we see voids now. And then the voids, as we can see here, is really huge. We see a tiny void on the RMA flux. And then on the water-soluble flux, there are no voids whatsoever. Now, what if a stranger walks up to you and then asks you, which of these three fluxes are the strongest or are more durable? I'm sure we will tell them it's the water-soluble flux, right? I know for a fact that I will tell them it's the water-soluble flux because I know for a fact that I do not want the components in my phone to fail or malfunction overall because I accidentally dropped my phone. I know that I do not want the documents in my computer lost because my little brother was running around and accidentally kicked my computer to the ground and the components in it failed. Now, using the water-soluble flux, we can then enhance the strength of this material. Now you may ask, what is the real repercussion of not considering using the right flux? There have been many cases of fire incidents from televisions because of poorly soldered PCB boards in televisions, phone, etc. Now, when the electric circuit or track on the PCB board is not well ignited, it can then lead to a fire incident. I will show you a short video of me soldering a PCB board using the tin zinc bismuth solder alloy along with the water soluble flux. Alright, yeah, here it comes. So using this PCB board, we can then see how I carefully soldered the specimen. The PCB board. Now these are the electric tracks, as I mentioned. If they're not properly ignited or the right flux isn't used, it could eventually lead to a failure in the PCB board, which could cause fire. So now using the tin zinc bismuth solder alloy, we use the soldering iron to generate the heat to melt it. And dipping it into the water-soluble flux, we then carefully solder the specimen together. You can carefully observe how I carry out the process. Now, in conclusion, we can now see that water-soluble flux is the strongest and most durable of all the fluxes I mentioned. And on application in our phones, tablets, computers, we can then be able to sustain them and have them last a lot longer. Just as I promised in the beginning of my presentation, most of you all now have become somewhat of experts in this field. And that is the end of my presentation. Thank you very much.